Hey everyone, it's Chaz. Welcome back to the channel. Hope you're ready for another coding challenge because in this video, we will be looking at LeetCode problem 51, N queens. This is actually going to be the first hard problem that we do on the channel, but honestly, this problem, it's not hard because of the algorithm that we're going to implement. It's listed as hard because it turns out there are a lot of steps involved in solving this particular problem. So the N queens problem is a classic computer science puzzle. It's why I wanted to show it on the channel. The difficulty arises more in the fact that we're talking about queens in chess. And so you have to know how to implement some of the rules of chess in order to solve this problem. And I think that's where the difficulty lies. But I'm going to do my best to explain this and show it to you visually, show you how the algorithm works. And hopefully you'll be able to follow and you'll be able to solve a LeetCode hard problem with me today. Let's look at the problem. The N queens puzzle is the problem of placing N queens on an N by N chessboard such that no two queens attack each other. Just to break out of the algebra here, what they're saying, let's say that N is 8. So that means we have an 8 by 8 chessboard, just a standard regular chessboard, and they want you to place 8 queens on the board in a way so that none of those queens can attack each other. Or if it were, say, n equals 4, then you want to have a 4 by 4 chessboard and set up 4 queens so that none of those queens can attack each other. And then it says, given n, integer n, return all distinct solutions to the N queens puzzle. And you may return the answer in any order. What will happen is, for some of these chessboard sizes, there's going to be more than one solution. We are being asked to provide all of the solutions, not just one of them. And then finally, at the end, it says each solution contains a distinct board configuration of the N queens placement, where Q and the dot or the period both indicate a queen and an empty space. So to show you an example, I'm going to look at the image here for example 1. So this is the case where n equals 4. So we have a 4 by 4 chessboard and we're placing 4 queens. As it turns out, there are 2 distinct solutions. And they're asking us to return this solution in the form of a list of strings where you represent a queen as the letter Q and an empty space as a dot or a period. If you look at this list of strings here, if I lay it out vertically, instead of horizontally the way it is here, you could see that the layout is exactly the same as what you see in the picture. There are Qs in my list wherever there's a picture of a queen, and there's a dot everywhere that you see an empty space. And because there could potentially be multiple solutions, it won't be enough to just return this list of strings. We actually need to return the other list of strings also. So it's like you have to have a master list that contains each list of strings. So it's not just a list of strings, it's a list of strings. So we'll have to come up with a way of submitting multiple solutions to the N queens problem before we return the master list. And then finally, at the bottom of the problem, they provide the constraints, which are pretty straightforward. The N in the N queens puzzle will be anywhere between 1 and 9, including those values. So we need to come up with a solution that will work for 1 queen on a 1 by 1 board, just a single square basically, and also 9 queens on a 9 by 9 chessboard, and also all of the whole numbers in between. So we are going to solve this problem using recursion, and we're going to use it with backtracking. Now, I'm not going to go into huge detail about what recursion is because I've actually already made a video about it. And in this video, I explain recursion and show you a few different practice problems that I go through visually and with code. So if you're still a little shaky on recursion, please watch that video first because I think it'll do a good job of explaining recursion for you in a way that it will help you understand how to now add backtracking to it. But basically in that video, I say that recursion is the use of a function that is defined in smaller, simpler versions of itself. Or in other words, if you're coding with recursion, you are using a function that calls itself inside of the function. Okay, so we perform our recursion. So what about the backtracking? Backtracking is going to be a technique that uses recursion to build up a solution one piece or one path at a time. One common way to think about backtracking would be, say you had a robot that was trying to move through a maze. What you can do is you can just try a path And if it turns out that you reach a dead end, just go back one step and try a different path. Try the next available path. And if that doesn't work, you just keep working backwards until you can successfully find a path, and eventually your robot will reach its destination. So like in the case of this 10 queens problem, we are going to build up a solution that starts with one queen. We're going to then add another queen to our solution. And whenever we can successfully add a queen, we'll just move ahead to adding the next queen. But we might find a situation or a path where placing the next queen is not possible. So if a certain path does not solve the problem, the algorithm abandons that path, it backtracks, and tries a different path. And so every time we successfully place a queen, we can move forward. Every time we find that it is impossible to place a queen, we go back one step. And we do this until we can find a way to place all of the queens on the chessboard. And at that point, we have a valid solution, and we can submit it as part of our master list. So in order to solve this problem, you have to know how queens attack in chess. And I think this is where most of the difficulty comes from in this problem. In terms of like a two-dimensional array, queens are attacking each other or attacking any piece in chess if that queen is on the same column as the other piece, or if the two queens are on the same row, then they are attacking each other, and also if they are on the same diagonal. And in fact, it doesn't only have to be the center diagonal, it can be this diagonal. And it doesn't have to be going from left to right either. This diagonal also would be considered attacking. So the difficulty in this problem is less so the recursion and more in implementing the rules of chess. Right, before we work on the code for this solution, I'm just going to show you what the recursive algorithm looks like along with the backtracking. So I have a partial chessboard here, 4x4. I know that in Java we use zero-indexed arrays, but for the sake of simplicity, I'm actually just going to call this row 1, row 2, row 3, and row 4. And then for the columns, I'm also just going to say column 1, column 2, column 3, and column 4. When we actually code some Java, we'll go back to using a zero-indexed array. So the way our algorithm is going to work, it's going to start in row 1, and then in row 1, we're going to try to place a queen in column 1. Now, anytime we successfully place a queen in a row, what I mean by that is anytime we place a queen in a square where it is not being attacked by any other queens, that will allow us to move on to the next row. Now, there's only one queen on the board right now, so obviously it's in a safe square. So we will move to the next row. And in that row, we will attempt to place a queen in the first column. Obviously, this isn't going to work. It's being attacked by the queen right above it. So we will just iterate to the next column. We won't backtrack yet. We'll just go try the next column. We move to the next column. It's actually still being attacked. So we try the next column, and this is a safe square. So that will allow us to move on to the next row. So we try to place a queen in row 3. In the first column, it's being attacked. Move to the second column, it's still being attacked. Third column, still attacked. Fourth column, still attacked. And we have actually run out of columns. Whenever we run out of columns, this is where we will backtrack to the previous row and try this queen in the next column. So we will just move this queen over. This is actually another safe square for that queen, so we will move on to the next row. Try to place a queen here again. It is being attacked. We go to this square, and this square is actually safe. So now we can move to the fourth and final row. We place a queen in the first column. It's being attacked. Here it is also not safe. It's not safe here either. And it's also not safe here. So we have run out of columns. So we need to backtrack. We go back to row 3 and move this queen. Well, that's not a safe square. And that's not a safe square. So we have run out of columns again, so we need to backtrack again. So we backtrack to this queen, but this queen doesn't have any squares left. So we need to backtrack again to the first call and move this queen over by one column. Now, since this is the only queen on the board right now, it's automatically safe, so we can move on to the next row. We'll place a queen in row 2. That square is not safe, not safe, not safe, but this square is fine. So we'll move on to the next row, place a queen in the first column, and actually the first column is safe. So we can move on to row 4. That square is not safe. That one's not safe, but this one is safe. So we have actually completed the board at this point. So now what? What'll happen is we will establish a base case where if we successfully fill all 4 rows, then we will submit this as a solution to the problem. We'll add this to the list of solutions, essentially. Now, we know from the example that for a 4x4 board, there's actually 2 solutions. So we've only found one of them. Our algorithm's actually not going to stop here. All it's going to do is submit this list as a solution, but it's actually going to keep going. So essentially what it's doing is it goes to a 5th recursive call, almost like it's trying to go to row 5, but it's really not going to row 5. When it passes row 4, it realizes that we have a solution, so it generates a board for that solution. And then when that call returns, it goes back to the 4th call, so that means we're right back in the 4th row, and this queen is actually going to move to the next column. It turns out this column is unsafe, so we'll run out of columns in this row, so we'll end up backtracking. This queen actually will not have any safe squares, so we'll have to backtrack again. This queen has run out of columns, so we'll backtrack again. We're back in the first row. We'll move this queen over. That queen is safe, so we can move on to row 2. That's a safe square, so we'll move on to row 3. Not safe, not safe, not safe, but that square works just fine. Move on to row 4. That square is not safe, but this square is safe. We actually just found another solution. We will submit this as a solution, so we'll add this to the list of solutions. We now have 2 on our list, which is what we were expecting. So at this point, we've actually solved the problem, but our algorithm does not know that. It's actually just going to keep going. So let's just see what happens. So when it returns from submitting our solution, it will actually go ahead and move this queen again. That's not a safe square, and that's not a safe square. So we run out of columns, so we backtrack. This queen also runs out of columns when it tries to move over. So we backtrack again, and then none of these squares are safe. So we backtrack again, and then this queen moves to the 4th and final column in row 1. That square is safe, so we will add a queen. That square is safe, so we'll add another queen, and then this queen is not safe until it reaches this square. And then we go to the 4th row, and then none of these squares are safe. So we run out of columns. So let's backtrack. That square is not safe. We run out of columns again. We backtrack again. That square is safe for this queen. Move on to row 3. And then none of these squares are going to be safe. So we run out of columns. Backtrack. That square is not safe. That square is not safe. We run out of columns, backtrack to the 1st row, and this queen has run out of columns. So in this case, our very first call is now complete. And so we can submit our solution, which contains a list of 2 valid chess boards. What did I say? Chess boards. So because this problem is so complicated, we've already taken a lot of time to explain the algorithm itself with no code. I'm actually just going to stop the video here. We're going to break this up into 2 parts. And in part 2, we will finally code this algorithm using Java. So that'll be it for part 1 for this video. Thank you very much for watching, and I'll see you next time.